So I wish to welcome you all. We'll be starting within a few seconds. I believe that we have the majority of the attendees already logged in, and I think it's a good time to start. So good afternoon or good morning, ladies and gentlemen. Welcome to this workshop about the off-grid system design by JinkoSolar's Sub-Saharan Africa team. This webinar is sponsored by JinkoSolar, the leading global energy company that is active in the solar PV, energy storage, among other applications in renewable energy. If you were not able to attend this session here on Zoom, or if you have friends that cannot log into Zoom, then they can watch that on the Facebook page, the official page of JinkoSolar Sub-Saharan Africa team. You can find it on Facebook, JinkoSolar SSA, and you can watch it in there. We'll be definitely recording this session, so you could watch this on YouTube afterwards, and we'll send you the link as long as you are registered to this webinar with your email. First of all, a couple of organizatory topics. I want to make sure that you can hear me well. Please write me in chat if you could hear me well. And okay, I get yes, thank you. And please introduce yourself in the chat so you guys also could communicate, socialize, and make some good business contacts today. Thank you for that. So where you send the question on chat, please don't send questions to the speaker today. If you have any questions to our speaker today, then please send that in the Q&A section. And if you are watching us on social media, then please send your question as a comment under the video. Then you could, our team will pick that up and we will be asking the speaker in the end of the session. So we'll go through a session, and 15 minutes in the end will be allocated for Q&A to have you all covered with the questions. Actually, the importance of today's session is because using off-grid technology to generate electricity will help us to reduce the consumption of fossil fuels, and this will help us to minimize the negative impact on the environment. And I think especially now with this Russian-Ukrainian war and the increased oil and gas prices is another very good reason to look into the off-grid solutions more seriously, as this is not just good for the environment, but also good for the pocket, because we can save a lot of costs when we reduce the dependency on fossil fuels and we depend on solar energy and energy storage for these applications. And that's exactly the topic that my speaker will be covering today. So I'll start quickly with the introductions. My name is Munif Barakat, and I am from Solar Arabic, which is the most visited renewable energy platform dedicated for the MEA region, the Middle East and Africa. And today I'm pleased to introduce again for the second time our speaker, Mr. Samuel Aremo. He's the technical services engineer at the Sub-Saharan Africa region at JinkoSolar. Samuel Aremo is an electronic and electrical engineer with experience in the renewable energy industry in Nigeria and Sub-Saharan Africa. His experience in the renewable energy sector has been accompanied by a vast knowledge of projects majorly in the mini-grid deployment across Nigeria, where he had been part of and also overseen the development of several renewable energy projects in Nigeria. He is currently involved in technical support for many projects in Sub-Saharan Africa, and he'll be covering today an introduction to JinkoSolar's products and solutions, an introduction to the off-grid systems, and some hands-on off-grid system design training that I hope that everyone will find it useful during today's session. Before I hand over to my speaker today, I'd like to get to know you better, our dear attendees. So we're running a couple of questions on the screen. You might already see the first one on your screen if you are on Zoom. I would like to know from what region or country you join us. If you are on social media, then please write just the name of your country as a comment under the video and the live stream. So we'll be happy to know from what area you join us today. I think the biggest, let's say, actually, I see that there's equal, let's say, presentation, but around 20% between Western Africa and Eastern Africa, Southern Africa, Northern Africa, and the Middle East. And we have a few people from Central Africa, Europe, and Asia, and some other regions as well. Thank you all for participating in this vote. And we'd like to ask you one more question. So please tell us from what industry you joined us. So do you work for a developer or an EPC company, an installer? Do you work in the public sector or as a consultant? Would like to learn more about you. I'll give it a few more seconds. Knowing your industry will help us to tailor the content as we move forward. I see that we have, like, let's say, a few equal categories, around 17, 18%. We have from developers, EPCs, service providers, O&M, and consultants. And at less percentage, we have independent consultants as well, and public sector participants. So you are all welcome to join us, and thank you for being with us today. We've got hundreds of people attending the session today, and for that, I'd like you, please, to invite you to ask your question as early as possible in the Q&A section. So we'll prepare for that, and we answer that in the end of the session. So without further ado, I'd like to hand over the session to Samuel to walk us through the off-grid applications, and we'll get back to you later in the end of the session in the Q&A section. Samuel, the floor is yours. Welcome on board.
Good morning, everyone. I'd like to appreciate everyone for joining this webinar today from Europe, North Africa, West Africa, and let me start by showing my screen. Muniz, thank you for the introduction. And
thank you.
Today we'll be talking about off-grid system design. And so these are the things we'll be covering today. First, to talk about just to introduce JinkoSolar to people who don't really know about JinkoSolar. Then we'll look into off-grid systems, then design, and also overview of the system. So first is that JinkoSolar is a leading global manufacturer, and we've been leading shipments for the past 4 years. And we are the first solar company in the world to deliver over 100 gigawatt of modules, and also have a global market share of 12%, which is the first in the world. And also we have an annual module capacity of 50 gigawatts. And also JinkoSolar is a company that really invests much in research and development, which is R&D. And with this, we've broken over 19 world records in cell and module efficiency. Also, JinkoSolar has diversified its product to solutions, and recently we started providing solutions such as the ESS, which is the energy storage system. We also provide solutions for solar lighting, solar pumping, and also for building integrated photovoltaics. That's for buildings. And for our ESS product, we actually have 3 segments, which is the residential storage system, the C&I storage system, which is commercial industrial storage system. We also have for utilities projects. So we actually categorize this system based on the storage. That is the battery side. So basically for residential solution, or let me say for home solution, we have between 1 kilowatt hour to 50 kilowatt hour. Then for C&I, we have between 50 kilowatt hour to 1 megawatt hour. Then for utilities application, mini grid, and for systems for grid purposes, we can have a backup of, or let's say, storage of over 1 megawatt hour. So moving ahead to the deal of the day, we'll be talking about off-grid system, and sorry, just a minute. About off-grid system, and just to give a brief highlight of the applications and what is off-grid system. So first is that any installation that does not is not connected to the grid, to the national grid or to the main grid, it's an off-grid system, either by not charging from the grid or supplying to the grid. So where are this system applicable? One is that for solar home systems, in most homes, especially in Africa, or let's say in most rural communities, you see people installing off-grid system. People that are not really connected to the grid also have the mini grid. Mini grid is also a type of off-grid system. In this scenario, there is no grid, it's just a centralized grid, which is the mini grid. Also, for telecoms company, you see that in rural areas or even in municipals or cities, you have telecoms mast depending on off-grid system, just solar, batteries, and also sometimes you have generators. Also, for solar water pumping, this is a DC coupled solution where you have solar panels connected directly to the DC pump. Also, for rural businesses, solar lamps, the small solar lamps you see all over the places, they're off-grid systems. Street light, vehicle charging, and traffic signs as well. So just to give a brief highlight about what is on-grid solar system and also what is off-grid solar system. One, for on-grid solar system, this system that connected to the grid. So you need to synchronize your system, your solar system, to the grid for it to produce power or give power to the grid or even consume back to the consumer. Also, in this scenario, you can export excess power. So if you have a solar power system in your, let's say in your office, in your house, if you have excess production, you can actually sell this. If you have something called net metering, so you can actually sell the remaining the excess energy back to the grid. And when the grid is down, one of the issues with our on-grid system is that because of anti-islanding, when the grid is down, your solar power system stop producing power as well. So it doesn't feed back to the grid. So when the grid is down, it also comes down as well. Also, there's a low maintenance cost and also low installation cost. The system is simple with few equipment. You just need your grid-tied inverter and also your solar panels. Then for off-grid system, so actually you don't need any connection to the grid. Just it's independent of the grid, like I said earlier. And in the case of the grid being, like backup in on-grid system, in this scenario we use batteries. So for off-grid systems, you can actually use batteries for backup, or in some cases, generator. And when it comes to grid failure or shutdown or grid collapse, off-grid system are not affected by these scenarios. And maintenance and installation costs are more expensive when you compare to on-grid system. Yeah, sometimes the system might be complex because you have more equipment compared to on-grid systems, and also for off-grid system, there's no electricity bill, so you don't have to pay bills. Even if there's an increase in tariff, you are not likely affected by the agreement in tariff. And also, we've been talking about climate change, and for on-grid system is that you actually reduce the carbon footprint, because for on-grid systems, you are coupling your system to a source being powered by, let's say, coal, or let's say carbon dioxide emitting sources. So actually for off-grid system, you're actually reducing the carbon footprint. So what are the components? What are the components of an off-grid system? One, which is the main source of energy, or let me say the main source of power, is the solar PV modules. Modules produce energy from the sun. So they harvest sun energy and convert it into electricity for our consumption. And also, two is we have the hybrid inverter or battery inverter. So for off-grid system, we have this type of inverters. Basically, either you have a hybrid inverter. An hybrid inverter contains the battery inverter itself and also the solar charge controller. So the solar charge controller is embedded into the battery, to the hybrid inverter. Or if you want to go for the other one, which is the battery inverter, you also need a charge controller. Then you also have the batteries and generator, which can be optional. So let me go through it again. You have your solar PV modules, which is the main energy source. You have your hybrid inverter, or in other cases, you might have your battery inverter and also your charge controller. Then also you have your batteries for backup, and also generator, which is optional. So looking at the system configuration, so mainly we have two types of system configuration. One is that we have solar PV with batteries and optionally generator. We can see in this scenario that let's assume the generator is optional now. We have the main power source to be to be solar panels. Then we have our hybrid inverter. The hybrid inverter converts, the power produced by solar panels actually DC power. They travel in one direction, they move in one direction and go that way. Then the hybrid inverter converts, from DC power source, from DC energy or let's say DC power to AC power for consumption. And also, like I said, the hybrid inverter has a solar charge controller embedded in it. So in this scenario now, we don't need an external solar charge controller. They can say also this hybrid inverter also charges the battery through the solar charge controller that is embedded in the inverter. And we can also see the electric load here, which is connected to the inverter. And you notice that in most industries, offices, they made huge investments on diesel generator. And let's say they want to go off grid, it might not be economical, to totally remove the diesel generator they currently have installed. So one of the system or one of the configurations to do in this scenario is to have a PV diesel hybrid system, which in this case we have a PV inverter. A PV inverter, and a PV inverter converts connected directly to the solar panels, or let's say the solar array, and convert this power to its power for consumption. So, but in this case, the PV inverter is a grid follower, so it can't produce or it can't process power without having the grid reference. So in this case now, the generators that's already being installed will provide grid. They are called grid former. You can also have a battery inverter with some small batteries to provide grid for grid parameters like frequency and voltage for the PV inverter to work. Also, you see that if you have this system, actually reduce, rather than facing off the total diesel generator, which the company or the industry have made huge investment on, to actually reduce our cost on probably diesel or fuel. So for industries such as that, I actually like to prefer PV diesel hybrid solution for them. Then also, let's go into designing an off-grid system. So today we're looking at a small office in Lagos, where I'll be designing an off-grid system for them. So what are the steps in designing a solar off-grid system? One is that you have to conduct a thorough site assessment and also an energy audit. Each step is very important. If you miss the first step, you might eventually end up with a very bad solution. So conducting a very thorough site assessment and energy audit is very, very important. So in this, I'll still go into that. Then two, you have your load estimation. You calculate your energy, you size your battery bank. After sizing your battery bank, you move into the hybrid inverter sizing, or if you have, if they are going to use a battery inverter, that means you have to size for also the charge controller as well. Remember, I said that an hybrid inverter has an embedded solar charge controller inside it. Then you calculate your solar energy requirement and also your solar module calculation. So moving to site assessment and energy audit, what are the things that you need to do in this scenario? One is that you need to actually ensure that do they really have the space to install these modules? What kind of installation are you going to have? It's going to be roof mounted, it's going to be ground mounted. So you check the available space. Also, you need to note the location of the geographical coordinate of this location to check on the tilt angle, the solar, the solar capacity of the environment, such as the radiance and other parameters of the environment, radiance, temperature, and the likes. And also, two is that you conduct energy audits. So there are three basic means to really know how much energy is being consumed by this firm or by this our small offices actually looking into today. So one is that for bigger industries, it might actually be difficult to start counting the number of equipment or appliances they have in that office or in that industry. So our best bet in this scenario is to install what is called an energy meter. So you can install this for, let's say, a day, or you can install up to a year, so a month, a year, 2 weeks, to capture the energy they truly consume in that duration. And from this, you can actually analyze your data to know what is the peak load, what is the average load, what is total energy consumed from probably 8 in the morning to 4 p.m. in the afternoon, or the energy consumed at night. So from these results, you're able to actually efficiently size your system. Two is that you can actually also understand the energy or the load consumption pattern with the electric bill. On the electric bill, you'll see the total energy consumed in a month per week, and from that, you can actually understand or know the energy consumed per day or per hour. And also the third one is actually for small offices or small industries or for homes actually can do a manual calculation. So in this case, you actually list out the equipment. They have a fridge, they have fans, they have TVs. So you list out the equipment, and you also list out the wattage of the equipment, which will actually show us in the next slide. Also, another thing is that you need to understand the user requirement and budget. Sometimes though the office, or let me say the industry, might want to go fully off grid, but the budget might not be able to cover for the solution. So also how to understand what is the budget of this office or for the client. And also in some cases we have different application scenario which are demand response, backup power. So you need to understand what actually they need this solar off-grid system for. And also, so one of the things is that if actually the budget cannot meet up with the solution, so the best thing to do is to separate the critical loads from non-critical loads. And after that, also do what is called a load separation. So you put the critical loads or non-critical loads on the probably off-grid system, and actually move the others to public grid or other sources of energy. So one is design flow. So actually, I'm trying to explain in two scenarios here. Case one is that what are the steps? What is the flow you follow when designing an off-grid system? One, the most important thing in case one is load requirement. So when you go for audit, you install the data logger, you go for manual calculation or manual inspection. And so you understand the load pattern, the load consumption. So the next thing to do is to size of battery, size of battery bank, or let's say your backup energy. So after that, you also move into your hybrid inverter sizing. And in the same way, you probably want to have a battery inverter or a charge controller separately, and you size your battery inverter. And after that, you move into your solar PV sizing. And one thing I actually tell people is that you don't actually size your inverter based on the load requirement alone, because for in the case of hybrid inverter, because remember that hybrid inverter also has an inbuilt charge controller. That means the inverter also charges the battery, and the solar means to the inverter, it's seeing both the load actually and also the battery itself as a load. So you need to consider the charging of the battery as well when you are sizing your inverter. And also your solar PV panels, like I said, is the main source of energy in this scenario. So that means as it's supplying the load as well, it also needs to charge the battery. So you need to size up solar PV based on the load requirement and also on your battery size. Then two is one is looking at for case two is that you're looking at the roof space. Apart from our budget or user requirements, in some scenarios, let's say the load capacity exceed or the solar PV exceed the minimum or the available space. So that means you're actually your major focus or your starting point to be from the available roof space. Then when you calculate how much panels, let's say how much PV can this available space occupy, then from there you move into sizing your hybrid inverter, also your battery size, and also in this scenario, since your available space, the solar panels installed, we're able to meet up with the load requirements. You actually have a load separation for critical loads or for non-critical loads. This is a small load estimation. So we'll be using, like I said, we have three methods. Is that install the data logger, do the electric bill, also you do a manual calculation. So this is a small office in Lagos, and I've listed out the appliances here from fluorescent up to fridge, printer, and scanner. And actually, next column is the quantity. So you need to list out the number of appliances they have in that environment or facility. Then also the power rating of each equipment. For fan, we have 128 watts. For the scanner, we have 100 watts. For the fan, we have 90 watts as well. So also the next thing to do is for conventional sake, we convert from watt to kilowatts. So we have the kilowatt values. Yeah, and also I like to say that solar power actually is a variable renewable energy source. That means it's actually not available all the time. That means it available, let's say, in the morning and at night time, there's no sun. That means solar panels cannot generate energy. I like to actually segment my calculation into two daytimes. One is from 8 to 4 p.m. That is from morning to evening, then from 4 p.m. to 9 p.m. Because I know that from 4 p.m. to 9 p.m., my major energy source will be my batteries. Or in the case where you have a generator, that means from 4 p.m. to 9 p.m., the main energy source is going to be a battery or generator. So I've said that in the morning, so they use their fan for 4 hours in the morning from 8 a.m. to 4 p.m. The fan is being used for 4 hours and up to the fluorescent bulb. And at night in the evening, from 4 p.m. to 2 p.m., I've also listed the number of the duration of consumption here. And the next tab here is the kilowatt hour, the energy consumed between 8 a.m. to 4 p.m. So if we do 1.44 multiplied by 5, we have 7.2. That means the energy consumed by the fluorescent bulb from 8 a.m. to 4 p.m. is 7.2. Then in total, we have 31.7 kilowatt hour during 8 a.m. to 4 p.m. Then at night as well, we have 11.8 kilowatt hour. Now, like I said, if you have a battery backup, that means your solar panel or your solar array has to meet up with the load requirement. That means your load has to be able to supply your load during the day, and also during the day charges your battery for night consumption. So the solar panel charges the battery, store excess energy into the battery during the day when sun is available, and at night to take out from the battery. That means you have to know the total energy consumed during the day at night. For the solar panel, the solar array has to meet up with the total energy consumed by the firm, or let me say by the office. So in this case now, if you add up 31.7 kilowatt hour by 11.8 kilowatt hour, you have 43.5 kilowatt hour. Like I said here, so also I added up all the kilowatt rating of the appliances, and it sum up to 8.1 kilowatt. That means the maximum power is actually 8.1 kilowatt. Then daily energy used, that means the daily energy consumed during the day at night is 43.5 kilowatt hour. Then the energy consumed from 8 a.m. to 4 p.m. is 3.7 kilowatt hour. Then the one consumed from 4 p.m. to 9 p.m. is 11.8 kilowatt hour. Then before we go into battery sizing, I'd like to explain some battery terminologies. And one is nominal voltage. This is the operating voltage or let's say the rated voltage of a battery. In most scenarios, you see things like 2 volts, 6 volts, 12 volts, 48 volts. And these are regarded as low voltage batteries. Then we have high voltage batteries like 100 volts and above. We also have nominal capacity. This is actually expressed in amp hour. It expresses the average amount of current the battery can actually give out or can take in under normal use. So in this scenario, that's something like 50 amp hour, 100 amp hour, 10 amp hour. Also have the energy, nominal energy, which is total amount of power the battery can deliver over time. And this scenario is noted as watt hour. We also have the cycle life. The cycle life of the battery is a very important factor of the battery. And I'm still going to explain about cycle life in the next slide. Also, we have DOD, which is known as depth of discharge. It should denote the amount of energy that's been removed in a battery. And also, apart from that, it also denotes the maximum depth you can reach in a battery. So most manufacturers will tell you that you don't go beyond this percentage. That's recommended DOD. And for lithium-ion batteries, you have between 80% to 90%. And for lead-acid batteries, you usually have around let's say 40% to 60%. And also the SOC of the battery talks about the state of charge of the battery. For example, let's use our cell phone, for example. Let's say your phone is on 70%, and the SOC of that battery of your phone is 70%. And the DOD is 30% because you've discharged 30% from it. And I'm going to explain using a diagram here. We can see that when you have 100% SOC, the DOD is 100% because you don't naturally discharge anything from the battery. So I wrote the formula here. SOC is equal to 100% minus DOD. You can also have DOD equals to 100% minus SOC. So they are interchanged. So if you have SOC of 90%, that means your DOD is 10%. Also, if your SOC is 0, that means you've totally discharged your batteries 100%. And yes, just to understand what actually DOD means mathematically. For example, let's say you have a battery of 3 kilowatt hour, which is 3,000 watt hour, and the manufacturer says the allowable DOD for this battery is 90%. That means the usable capacity you can use in that battery will be 0.9, which is 90% of 3,000 watt hour. And in this scenario, we have a 2.7 kilowatt hour, rather 2,700 watt hour. And one of the important parameters of a battery is the C rate. The C rate is a measure of the rate of discharge, or the amount of charge or discharge you can actually take out from a battery relative to its capacity. In most scenarios, when people buy, let's say, battery of 100 amp hour, people say this battery can discharge 100 amps in 1 hour. It's actually not be correct, because the C rate actually tells, like I explained there, we have 50 amp hour. This 50 amp hour can actually can mean so many things. Can mean 50 amp discharge in 1 hour, or can mean 25 amps discharge in 2 hours, or can even mean 100 amps discharge in 30 minutes. So to know the proportion of current to time, the C actually tells the proportion of current to time. Because remember that the capacity of the battery is expressed in current and time. So you actually don't know the proportion of the current to time. So the C actually tells you the amount of current the battery can discharge or can be used to charge the battery over time. So what is the formula for, so let's say you have 50 amp hour. So what is the formula? How can you know how much current this battery can give over time? One is that for current is that you have nominal capacity multiplied by the C rate. And the time actually is 1 over C rate. So I made a small example here. Let's say you have a battery of 48 volts by 50 amp hour. That means the rated voltage or nominal voltage is 48 volts. And also your nominal capacity is 50 amp hour. And the C rate is 0.5 C. Now, how many current, what is the amount of current this battery can discharge over time? So one, to get this is that you multiply your nominal capacity by 0.5, which is a C rate. You have 25 amp hour. And also the time rate will be 1 divided by 0.5, which is 2 hours. That means this battery can supply 25 amps in 2 hours, or can be charged with 25 amps in 2 hours. So you can actually say, when you see 50 amp hour, you can actually say the battery supply or will charge 50 amp in 1 hour. That might not be correct. Then 2 is the cycle life of the battery. So the cycle life of the battery actually is the number of charging and discharging cycles a battery can reach before it actually is end of life value. So in most scenarios for lead-acid battery, you have between 3,000 to, let's say, 600 cycles, and maximum you see probably 1,500 cycles. And for lithium-ion batteries, you have something above 4,000 cycles, 5,000 cycles, 1,000 cycles. And actually, the cycle life of the battery tells how long the battery will last. I've seen people, engineers, technicians say this battery can last for 5 years or 10 years. It's technically wrong, because what determines how long the battery will last actually the cycle life of the battery. Like I said, cycle life is actually 1 full discharge. A cycle, only 1 full discharge and 1 full charge. So let's say in a day, you have 1 full cycle in a day. And you have lead-acid battery that has a cycle life of 365 cycles. So let's say in a day, you have 1 cycle. That means 1 full discharge and 1 full charge. So that means you have 1 cycle per day. That means your battery will last 365 cycles over number of times you discharge that cycle and that battery in a year. So in a year, you probably have 35 cycles as well. That means your battery can only last 1 year before it actually reach the end of life. So let's say you actually discharge to 1 cycle a day. That means your battery would actually last longer than a year. Also, the cycle life depends on the DOD and temperature. So let's say manufacturer says the DOD of this battery is 90%. That means the cycle life will be at that DOD. If you discharge beyond that DOD, let's say for lead-acid battery now, the DOD is 50%, and the manufacturer says that the cycle life of this battery at 50% is 300 cycles. That means if you discharge beyond 50%, the cycle life of the battery will actually reduce. Also, temperature actually affects the cycle life of the battery. And here I have a small graph. We can see that at a very high temperature of 55 degrees Celsius, the cycle life of this lithium-ion battery has dropped to 1,000 cycles. And at 45 degrees Celsius, you can see at 2,000 cycles. We can see how greatly our temperature affects cycle life battery. So let's always ensure that we we make sure that our batteries are within the range of temperature as specified in the data sheet of the battery. So moving on into our battery sizing. So what are the requirements and the factors we need to factor in when calculating our battery size? One is the DOA, which I call DOA of autonomy. This is when you're estimating that there will be no sun, let's say for 2 days, 3 days. So you also want your battery to cover for days of low sun or bad weather. So in most scenarios, you have a day, 2 days, 3 days. Actually, the more the DOA you have, let's say you have 2 days, that means you have 2 times of the initial requirements. And 2 is the DOD, 3 is energy demand, and 4 we have the efficiency. So I'll be using a battery, and this is the battery, and the battery energy is 5.12 kilowatt hour. Nominal voltage is 51.2 volts, and capacity is 100 amp hour, and the circuits, number of circuits is 5,000 circuits, and the DOD is 90%, and the circuit is 1C. Then what are the other values we need? 1 is the DOA. I'll be using 1 day. Like I said also, I don't know if you know, in my previous webinar, I said that sometimes we have bad weather or low sun. So at that time, we don't want to lose power. So at that time, we want our battery also to cover up for low sun or bad weather. So also we'll be looking at sizing our battery to cover up for drop in energy produced from solar panel. Like I said in this formula here. So the energy required from the battery will be 11.85, which is the nighttime consumption. Permit me to go back. Like I said, nighttime consumption is 11.85, and remember that the maximum power is 8.18 kilowatts. So I want my battery to cover also for 1 hour 30 minutes during the day. There's no sun, or there's no energy produced from the solar panels. So I want my battery to be able to cover for at least 1 hour 30 minutes of maximum capacity, which is 8.1 kilowatts. So in total, the energy required from my battery will be 24 kilowatt hour. Now this is the formula I'm going to determine the number of batteries I need to make up. Remember I said that we're using a battery of 5.12 kilowatt hour. I'm going to make up 24 kilowatt hour. Now, what is the formula to get the number of batteries you need to use? So the formula is number of batteries equals to energy demand multiplied by the day of autonomy, which is 1 day, divided by the battery capacity, that's the energy capacity of the battery, by the DOD and also the efficiency of the battery. So we have this simple calculation here, and we can see that we have 5.78 batteries. And actually, we can't have a half battery or 0.78 batteries. So we can actually go for 5 or 6 batteries, depending on the budget of the customers. So in this case, now we're going for 5 batteries, and if you have 5 batteries, you have 5 by 5.12 kilowatt hour, you have 5.6 kilowatt hour. Also, moving on to the inverter capacity, there's something I would like to share with everyone. Like I said here, that the rated voltage for the battery is 51.2 volts. I've always seen that most inverters, they actually have a rated voltage, let's say 48 volts, 24 volts, 12 volts. What actually matters is the voltage range. So in this scenario now, the voltage of the battery is 51.2 volts. And for the inverter we're going to use, it's going to be a 48 volt rated inverter. But people will say it won't work. Actually, it will work because what you actually need to understand is that the inverter has to cover the inverter range. You've seen most scenarios you have let's say from 40 volts to 50 volts, or let's say 40 volts to 60 volts. Once the range, the battery rated voltage, or even the range of the battery is within the inverter rated voltage, then there's no issue. So in this scenario, we can also use the 48 volt rated inverter. And what is the function of the inverter? So one, in setting an inverter is that we have to consider that all the loads are being turned on. Normally in an office, you don't have all your equipment turned on, but you can never tell. So you need to size your inverter based on the total load, on the instantaneous load. That means all their load must be turned on. Like I said earlier as well, this inverter is an hybrid inverter. That means it has an embedded charge controller inside it. That means it also charges the battery. So we also need to factor in the load to the battery. So what are the factors we need? We need the maximum power, battery capacity. If you sized your solar panel first, so you need to consider the power keeping of the inverter. And also safety factor in case they want to expand they want to add more equipment to the office or to the industry, and also efficiency of the inverter. So what is maximum power of the office? The total load consumption, that is 8.1 kilowatt. Then the battery charging, I'm allotting a factor of 1.05. Then the safety factor is 1.25, and the efficiency is 95%. So I'm using this formula, which is the power multiplied by the charging factor and multiplied by the safety factor by efficiency. And I have 11.3 kilowatt rather. Then in this scenario, you can go for 10 kilowatts or 12 kilowatts. But in most cases, you actually see that the difference between the price of 10 kilowatts and 12 kilowatts is actually very, very small. So why not just go for 12 kilowatt hybrid inverter? So I'm going for a 12 kilowatt hybrid inverter in this scenario. So moving on to solar panel sizing. Before I go into sizing, I'd like us to understand how to, understanding solar panel specification with the data sheet. And I will be using a solar panel of 415 watt peak. And first is the STC. I consider STC. The STC is actually generated the tested values in laboratory. So one, we have the maximum power to be 415 watts peak. Then the maximum, the voltage at maximum load. When load is connected across solar panel, what is maximum voltage across the PV module? So that is 30.79. Also, when the load is connected with the maximum current, we have 13.48. And when there's no load connected across the solar module, probably in your inverter or your charger controller, there's no load connected at that point. The VOC, which is the VOC, open circuit voltage, we have 37.31 volt. Also for ISC, when you short the terminals of the PV, the current that will pass through. Also, one important parameter to note is this maximum system voltage. And in the past we have solid volts. Currently, we're expanding into 1,500 volts. We still have also 1,000 volt system voltage. Also explain what it means. It actually means the maximum number of panels you can actually connect in series. So in this scenario now, if you connect, let's say, some panels in series, the maximum voltage should not exceed 1,500 volts, as specified in this data sheet. Also, another important parameter is the temperature coefficient. And as you can see in this graph, the smaller the temperature coefficient, the lower the power loss. At higher temperature coefficient of 0.35, we have more power loss because at temperature actually affects performance of PV module. If you have high temperature, the performance of PV module is going to drop. Also at very low temperature as well. So you need to also consider what is the temperature coefficient of this PV module. So what does it talk about? It talks about how the parameters of solar panel changes with 1 degree increment or decrease in temperature. And in this slide, I try to explain that in Lagos, for example, the lowest ambient temperature ever recorded is 20 degrees Celsius, and the highest is about 35 degrees Celsius. And to know the voltage, at this temperature, very important to know the voltage at this temperature, because like I said, you must not exceed the maximum system voltage. So, for example, we're using a Tiger Pro module of 415 volts, and the VOC is 37.31 volts, and the temperature coefficient of that voltage is minus 0.28. Where did I get this value from? You can see from this data sheet, you can see temperature coefficient of VOC is minus 0.28%. So I've done a small calculation here, and we can see that at 20 degrees Celsius, the voltage has actually increased to 38.71 volts. And at a high temperature of 35 degrees Celsius, the voltage has reduced to 34.5 volts. So when you consider, temperature coefficients, you can see that if you don't consider, let's say you have you don't actually consider temperature of that environment. So you have 1,500 divided by 37.31. You can actually connect 40 panels in series to make up 1.5. And if you compare, if you consider the temperature coefficient, that means the maximum number of panels you can safely consider for a 20 degrees Celsius ambient temperature is 30 panels. 30 panels. So that is just to show the effect of temperature on solar PV modules. So next, let's calculate actually how much panels or our solar panels requirement. So what are the factors? First, select the PV module. What are the things you need to look out for? What is the warranty the manufacturer is offering you? 30 years, 25 years. What are the technologies? Half cell, bifacial modules, top con cells, PEC, and the like. So also, what is the pre-sales and after-sales services of this company, solar PV manufacturer like? So coming to calculation, what are the factors we need to consider? So one is total energy demand. Let me quickly go back to the previous slide. In our calculation here, we're able to say that our solar panel must produce energy during the day and night for day and night usage. For the night usage, it will be stored in the battery. So what is total energy required from our solar PV module? That is 43.5 kilowatt hour. So we have that as well. And that size is, like I said, power clipping is very important. For example, let's say you have a solar size of 20 kilowatt peak. That is a solar PV size, 20 kilowatt peak. And what is actually 8 kilowatts. The inverter can, let's say the inverter can actually take, you see in the data sheet that the inverter can take probably 12 kilowatts or 10 kilowatts. That means it's going to clip the excess power or excess energy produced by the solar PV. That means you shouldn't consider power clipping when sizing your PV or when sizing your inverter. And the efficiency, 90%, there will be losses along the line from the cable to the cell itself to the inverter, there are losses. So since solar panel is the main energy source, so you need to cover for the losses as well. Also, you need to understand, like I said in the previous slide, you need to understand solar profile of the environment, the tilt angle, the radiance level of the environment. I can actually get any the values from this website, Global Solar Atlas, and also I'll be using solar panel of 415 watt. So here's my formula: power requirement equals to total energy demand divided by the peak sun hour by the efficiency. So I have here that we have 4.35 to divide by 4 hours times 0.9. So we have a 0.1 kilowatt peak. So next, determine number of panels you need. So remember I said I was using a 415 watt solar panel. What solar panel? I need to make up to 12.1 kilowatt peak. So you need a total of 30 panels. And when you do that, you have 12.4. Because if you do this, you probably have like something like 29 points. I can have modules or 1/4 modules. So you go for the nearest, the highest number, not the lowest one, because you need to meet up with this 12.1 kilowatt peak. You can only do 12.5, 12.2, but you can't do lower. Let's say 12 or even 11.9. So we're going for 30 pieces, and we have a 12.45 kilowatt peak. So how do we configure our solar panels? So I'm showing the data sheet of this panel and also the data sheet of the inverter. So you need to understand that for you to string a panel, understand the basic requirement of the inverter and also the specification of the solar panel. And in this case, the VOC of the solar panel is 37.31 volts, and the ISC is 14.01 amps. So now looking at the data sheet of the inverter, you can see that the maximum DC input power, that means the maximum number of panels you can connect to the inverter, is 15.6 kilowatt peak in that scenario. And then the PV input voltage range is from 160 to 800 volts. MPPT voltage range, that means the charge controller embedded in the inverter operates at best between 200 volts to 650 volts. And also the input current, the maximum PV input current is 34. So before I go there, let me explain this. So number of MPPT strings per MPPT. So you have 2 by 1. That means you have 2 MPPT in this inverter, but one of the MPPT has 2 circuits. So you can connect 2 strings to MPPT of one circuit and 1 string to that circuit. So you have for each string, actually 17 amps. But because this other MPPT circuit can take 2, we have 34 amps and also you have 17 amps. So to string our panels, we need to consider one is the temperature coefficient of that location, so that the voltage of your panels don't exceed the maximum PV input voltage of 800 volts. So in this scenario, I'll be using just 650 volts. I'll be using 650 volts, which is thereby what's it called, the VOC, which is 7.31 volts. You have 17 panels, and like I said, we are going to use 30 panels. So we have if you have 17 panels, that's not up to our required capacity. So I'll be using a configuration of 2P 15X, which is 2 strings of solar array, and 15 of them in series. So looking at that, you have 15 multiplied by 37.31 volts. We have this total VOC or total voltage across the array. So you have 2 of them. You also explain how our stems.
If you please, we need to wrap up within a minute, please, Samuel.
I will do that very soon.
Thank you.
So just to explain, I said we have 2 arrays of 2 arrays of solar power. So we have this is the first array, goes to the first MPP slot, and the second one. Then we have 5 batteries, 1, 2, 3, 4, 5 connected in parallel. And also just to show you the components we've sized for our inverter, 12 kilowatt inverter, for the battery, 5.6 kilowatt hour, and for the solar PV modules, 12.45 kilowatt peak. And also for efficient sizing, just to optimize your sizing, you can actually use the software, which is PVist, SAM, Helioscope, and also OMA Pro. And just to show the battery we used, which is the 5 kilowatt battery pack, you can see the data sheet here. And you can also see the 3-phase inverter we are using, which is the 12 kilowatt inverter. So if you have any questions after this webinar, you can reach out to me at my email, samuel.aremu@jocosala.com. Thank you very much for attending the webinar.
Thank you, Samuel. I appreciate the presentation. I appreciate this hands-on, let's say, explanation and design of off-grid systems. That's something that's very important to get a good feeling, not just about the technology, how to use it, but also how to implement it in real projects. I'll get to we have 8 minutes left to go through some questions from the Q&A section. We received more than 20-something questions that would like to cover as soon as possible. I'd ask everyone to remain with us. All of those that asked for the presentation will be added to the same registration page, and you will get an email within 48 hours with the link where you can find the presentation and download it as well. Let me start with the first question that I have. How would you control, that's a question from Mr. Muafak made that, in off-grid systems, how would you control the voltage and frequency? If somebody are on mute.
Frequency of what? I didn't understand the question.
Yeah, that's how the question comes. Usually, like on grid, usually that's basically you the inverter would regulate that. Now, maybe we ask Muafak to send more details then to his question.
That be better.
I have a couple of questions as well, basically the same, asking what's the difference between AC coupling and DC coupling for energy storage.
Okay, so for DC coupled, the main reference point is the DC bus bar. That means you are coupling your energy source with DC bus bar. So in this case, we have the PV, solar PV, and also you have probably the hybrid inverter or a battery or a solar charge controller. With that reference, the DC reference. And for AC coupled, in this case, you have a string inverter. Let's say a PV inverter, or in most cases, you have grid inverter. So the reference, the immediate output reference of the solar PV, AC, AC bus bar. Then from the AC bus bar, it goes probably to, let's say, your hybrid inverter to charge the battery. So for DC coupled, you have just 2 stages of conversion, from DC to AC, and also from AC to DC. But in AC coupled, you have 3 stages. You have from DC to AC, from AC to DC, and also from DC to AC again. So that's basically the difference between AC coupled and DC coupled. And also, I actually recommend that for small systems, let's say below 1 megawatt, you can go for DC coupled solution. They're actually very efficient because you actually have small conversion processes compared to AC coupled solution. And also, when you talk about expansion, it's actually very easy to expand AC coupled solution because they're just expanding on the energy production side. So these are the basic differences between AC coupled and DC coupled solution.
Thank you, Samuel. Another question from Mr. or Ms. Taiwo Sanyaolu. Sorry if I don't pronounce the names properly. They ask if they would use PV system. So would you still need to connect the inverter to a grid? Just like that. So first question, and how does it help to save fuel if you need a diesel generator anyhow? I'm not sure, like if that's
okay. For generator, I'm sure that we understand that the consumption actually depends on the load connected to generator. So in case of a PV diesel hybrid configuration, during the day, actually running at minimum capacity of the diesel generator, let's say 30% of its capacity. That means your diesel consumption is actually going to will be reduced because your main energy source will be from the PV. Then at night, you also switch back to diesel generator. That means the diesel cost actually being halved. That means if you are consuming, let's say, 24 liters of diesel, might actually reduce to, let's say, 12 liters of diesel. So that has reduced your cost on the generator.
Thanks for that. I have a question from Mr. Brahim Benjama, who asks, in winter time, if there are, let's say, clouds for 3-4 days, no much sun, then how would you use that to in sizing the battery?
Okay, like I said, there's one factor I mentioned, which is this of autonomy, and which is you can say 2 days, 3 days, but actually going to increase your cost. And that factor is that we actually, when we are sizing our PV modules, we actually use the worst case scenario. That means the worst temperature conditions during winter. So the peak sun hour, actually is 4 hours, but actually you have more than 4 hours of sunlight in a day. So actually we've sized the PV to be on the worst case scenario. That means during winter or during rainy season. So to actually cover, also you can also expand your battery capacity, which is based on the days of autonomy.
Okay, and another question from Mr. Hijab. Do you usually use the trackers for off-grid PV systems?
Yes, but you need to understand the trade-off between one, when you use trackers, actually trying to to make your solar panel more effective. More the energy produced should be more than when I'm using any tracker. We're trying to do the trade-off between the money you're going to spend on tracker and also the energy you're going to gain from using tracker. So if the money you're going to spend on tracker, the energy you're going to get from using a tracker is more than the expenses in quote, then you can actually go for a tracker. But in small scale installation, it's very expensive to install a tracker. Energy actually tracking is very, very small. So you need to understand that the trade-off between the cost of installation and also the energy are going to benefit from using a tracking system.
Thank you for that. We still have time for 2 more questions, I think. I have a question from LinkedIn here that I see on my phone from Mr. Rashid. He's asked, what are the considerations taken for sizing the battery cables and protection circuit breaker with regards to maximum current and short circuit?
Okay, so I usually recommend that we follow IEEE current cable sizing. There's a table by IEEE you can follow. And also, I usually say that just for conventional sake, that you need to ensure that your cable size actually smaller, or let's say higher than your breaker size, so that when your breaker is, let's say you have a fault or overcurrent, your cable is not burning while your breaker is not tripping off. So you need to consider that your breaker has to trip off before your cable start burning. So you need to consider that as well.
Okay, let's say there is a question from Mr. Tariko Lemi. My question is about inverter. If we take inverter specification, example, maximum charging current is 80 ampere and maximum PV voltage is 450 VDC, but the maximum power it can handle from PV side is 6,000 watt. From theoretical knowledge, power is the product of current and voltage. If so, the max power should be 80 by 450, but why 6,000 watt is written on the inverter? I'm not sure if it took this from your example or not. If it is a different case, then I ask him to send an email to you to clarify that.
No problem. No problem.
Yeah, I think that would be a better idea. Then just one last question, because we get a couple of questions about inverters, and they're asking like what's the difference between their, let's say, on-grid and this off-grid inverters, just in general, or hybrid inverters. Just a quick summary from your side, please.
So on-grid inverters are inverters that can be connected to the grid or to the electricity grid, while off-grid cannot do the same. Well, hybrid inverter actually that's both purposes, on-grid and off-grid. So most hybrid inverters, in fact, all hybrid inverters can do on-grid and also off-grid.
Okay, perfect. And last, maybe a quick one from Mr. Abdul. He asked about the best simulation software to design off-grid systems.
It depends. There are several of them, so it depends on how vast we are with different softwares. We have PVist, OMA Pro, Uscope, and people enjoy different softwares. So I can't say which is the best.
Okay, great. Perfect. I think we're just on time. Thank you very much, Samuel, for this informative and useful presentation, the hands-on calculations. I hope people have learned a new skill today that will be useful for them in their jobs. Please follow the official Facebook page of JinkoSolar Sub-Saharan Africa. It is JinkoSolar SSA. The recording and presentation will be sent within 2 days to the same email address that you used to register to this webinar, so no worries about that. So I wish to, first of all, thank you all for attending this session. We had hundreds of people attending today, and I'm looking forward to meet you again. Thank you for all of your interesting questions and for making this, let's say, a two-sided discussion in this short Q&A section, and we will work into extending that in the upcoming sessions. Thank you very much, Samuel, for the presentation, for the very informative presentation. Everyone is asking for your presentation. We'll make sure to deliver it to them within the coming days. Have a good day, everyone.
Thank you.
Thank you.